Right. Okay. Today this is sort of a larger overview of self-supervised methods, and most specifically the bootstrap your own data method and the SimSiam method. We shortly talked about it in the notable work for NeurIPS, but yeah, we wanted to dig a little deeper. So this is where Alex starts, I think.
Yeah, I just want to show that people trying to solve object recognition, and there is multiple approaches how you can do it, and kind of this talk trying to summarize what people try to do to open Sesame so they can get better object recognition. We can switch next slide. So here we're showing for state-of-the-art methods in representation learning. So one of them is SimCLR, then it's SwAV, which is using some online clustering. Then we have BYOL, which is kind of similar to SimCLR. But it doesn't use contrastive loss, which trying to find similarities between views and doing in moving average fashion. And we'll have SimSiam, which kind of trying to summarize all these three other works, and we'll see how we can do it much simpler than using other three methods. So next slide, yes. So idea behind SimCLR is contrastive learning. So basically, you want to attract same view of image, like you want to attract same image but on different views. For example, you have a cat and you have some data augmentation on the image, and you want to say that representation of these two images, which is Z, will be should attract it. Like you want to attract this two representation together, and you want, so in denominator you want to calculate the normalization constant, which is built from negative pairs. Basically, you want to repulse dog and cat, or like next image from the batch. So the idea is like you're just trying to find, so you want to attract and repulse between different samples. So you want to kind of recognize the samples. And schematic of this method will be, you have an input image, you applying some random data augmentation, you get two different views of your original image, then you're passing through encoder F, and you're getting latent representation Z, and then you just computing as a similarity, cosine similarity loss. Okay, and then in SwAV you have basically a similar approach. You have same schematics, but you adding some align clustering. So you sampling not like negative pairs. You're sampling pairs through clustering. So you kind of can understand that you can understand it this way. For example, if you have image of a cat, you can create some prototypes which kind of summarizing this cat, and you can have prototypes which summarizing the dog, and this prototype of a dog will be negative for you. So you're basically trying to contrast the prototypes instead of just
prototypes.
samples.
Alex, the prototypes, are they in which space? Are they in the image space X, or like you're clustering the representations while you're learning? It's kind of difficult to read. Can you explain?
Okay, so prototypes will be in latent space. So everything happens in latent space. So instead of having a representation of other image as the negative sample, you trying to create contrastive learning through prototypes. And there's like a lot of multiple engineering steps. It's a lot of formulas, but basically, like the main idea here is that you kind of creating some code P as in SimCLR in some sense, but you're contrasting here with so you're contrasting with cluster or like prototype C, and then they also do some additional steps. I won't go like through whole idea of SwAV. It's another read, but I'm just saying this example shows that you can add clustering, and it will take a lot of effort to do so. And the future SimSiam will simplify this process, will simplify this framework. So you probably won't need it, even it's a nice idea. So like third method will be BYOL, which Eloy will describe in much more details, because it's like current state of the art, and it doesn't use like negative samples, and it doesn't use kind of contrastive learning in some sense.
Right. So that's basically the most important thing about Bootstrap Your Lane, is that this was a paper that said, you know, mining these negative samples can take up a lot of time. And can we do without sampling these negative samples? So is training a model that only has positive samples, is that still robust? And it turns out it is robust. And when it was published, it outperformed a lot of the state of the art. So it became the state of the art basically on ImageNet. So you can see like SimCLR is like a few percent lower on top one accuracy on ImageNet.
It's different from what Google reported in their conclusions for the year 2020, but just saying.
Okay, so how it works. So one thing to take away from this presentation is you don't need negative samples necessarily for self-supervised learning, although that has been like the standard, like triplet loss and like this sort of contrastive learning was very important. And the second thing is maybe simple solutions are better than very complex solutions, because as you're going to see, this is a more simplified solution compared to for example, SwAV that we discussed here. And SimSiam, which we're going to discuss after this, is even more simple. So, and it outperforms this work again. So basically, the idea is, I'm sorry,
yeah, sorry, could I interrupt real quick? I'm kind of curious what the difference in having two different parallel branches versus just having, you know, a wider network, and then, you know, having some functions to compare in between. Like, is there a difference in splitting it up like this and then converging it?
Versus, I guess you're learning, if you have a wider network, you're learning parameters for both views of the representation. So I think that's the difference here, is that you're only learning the parameters for one network. So the way this works is you have this network, which is called the prediction network, and you have this bottom one, which is the target network. But actually, the target network is the original prediction network. So if you would make this, or it's a moving average of the prediction network. So what happens is if you would make it wider, you would be learning parameters for both of the views at the same time, right? And here you're only learning it for the prediction part.
Okay. Maybe like maybe we didn't describe it very well. Like, what's the point of doing this? Like in the sense like Siamese networks? And I think we will have slide about Siamese network, and we can describe more why we need
Yeah.
this.
Yeah, we'll talk about Siamese networks after this in a little bit more depth. But I think so. I'll go through this one fairly quickly because it's anyway. So I'll just explain how it works. So what we have is an input image, and we try to predict the representation from the moving average of the same encoder. So what happens is each time you take a step to update your weights, there's a stop gradient here. So the weights in your sort of moving average encoder will not update, but the way it will update is through a moving average update. So it looks like this. So you take the parameter update that you're getting for this sort of prediction network, and you use a moving average to update the encoder that you're predicting, which is the target network, is what they call it. The reason they do it, because it sounds kind of complex in a way, the reason they use this moving average encoder as the target network instead of the same network twice with the stop gradient, because that's very important, is the stop gradient. So you don't update the weights of this moving average encoder, you only update the weights of this encoder. And the way you update these parameters is through the moving average update. So there's no gradient flowing back here. And the reason they do that is to make sure that it's robust and it doesn't collapse, like the representation doesn't just collapse to like 0, 0, 0.
Just a question, like along which dimension? Along the batches, along like the more, it's like what are you averaging? Along batches, right? So samples, training samples, or what?
No. So the parameter, so it's just the moving average update is just 1 minus tau times
1 minus, like, are you looking back
update
at previous batch that went
Yeah.
through the system? Okay, so you're averaging the batches, like as you go looking at the data. Or
No, you're averaging the parameters
gradients.
of the,
Yeah, you
the parameters of the other network. So the
parameters.
theta is the parameters of the prediction network. Psi is the current parameters. So at time step 0, the first batch, this psi will be just randomly initialized, and then we make a prediction. We update the weights of the prediction network, and then through this moving average update, we use the new parameters of the network, and we do an update where it's, it's sort of they will slowly converge to each other, but they will never hit each other, because this will always be like a more stable sort of network that lags behind the updates of the prediction network. It's like a sort of previous network state.
It's a momentum, but it's not on the gradient. Usually we do that with the gradient.
Right, exactly. It's a momentum straight on the parameters. Okay, so that's basically what happens. And so I just wanted to talk about like what has Siamese networks been used for before, because in a way you can see this as a Siamese network. I mean, it's not specifically a Siamese network, because that would mean that this network and this network are almost the same. But in this case, it's not, because this is the moving average of this one. So what have Siamese networks been used for before? The first Siamese networks was developed by Bell Labs and also with LeCun, who is known for CNNs, obviously. And what they try to do is do signature verification. So you have two of the same networks. You input two slightly different. So I don't know if you guys can see it, but slightly different signatures. There's some small differences here. For example, here you can see that the O is kind of different. Two slightly different signatures, and you have a threshold. You calculate the similarity between the two representations, and if it's above the threshold, you say that the signature is not the same, so it's not the correct signature. You don't verify it, and if it's below the threshold, you verify the signature. That's basically what they were used for previously at the very beginning. I think this is 1984 or something, 1994. I don't know, something before 2000, I think. What have they been used for more recently? So recently, there's been a large body of network to do object tracking. The way this works is you have a sort of sub window, so a small sub window, and you have a larger window. You have two of the same networks that extract features, and then you convolute this sort of small network over the features, and you get a score for each. Okay, I should explain it differently. Let's say you have a red square and a blue square, like here, two squares. To find where the red square is at this moment, you can just convolute like a red square over the image, and you get the score for each location of the. There's a good name for this. What's it called?
Coordinate?
No, I mean like. So if you want to find the red square in the image, you can
matching filter, right?
Right, a matching filter. Yeah, that's the name for it. That's what I was looking for. You could just create a photo of a red square and just convolute it over the image, and you get a matching filter. What you can also do is first you extract the features so that so you get a smaller space that you have to search over, and then do exactly the same thing, and you get a score in a smaller coordinate system, which is often faster, but it also tends to work better. And this is used for like object tracking. So in movies, you don't want to have two very big pictures that have to convolve over each other because it takes a lot of time, a lot of computational resources. So what they do is they extract the features using a convolutional neural network, which is the phi here. They're both the same. And then you do the convolution in the sort of feature space. And now Alex is going to talk about SimSiam.
Let's just ask question, is there any question about Siamese network or contrastive learning?
That was really clear. Thank you. That makes a lot more sense now.
Okay. Okay, we can go to. Okay. So the main idea behind SimSiam that knowing this three methods from previous work, we can remove some steps like removing contrastive learning itself using negative samples. And why we want to remove negative samples? Because SimCLR uses a really big batch, and you need a lot of negative samples to get a better signal. So, and there has been a lot of work which trying to evaluate problem with negative samples. They could create hard negative sampling. They could create some dictionary, where you're trying to accumulate as much samples as you can from previous iteration in the algorithm. So we can remove this negative sampling, and in SwAV they do online clustering, which is was trying to solve negative sampling problem in some sense. And in BYOL they completely remove negative samples, but you have additional momentum encoder, which is make your model to have much more memory usage during training, because you have to kind of having second pair of your neural network weights. And the main idea behind SimSiam, basically you have we keep the slide. We can have a gain prediction network as in BYOL, and instead of having momentum encoder, we just passing second view of an image through same encoder, but we're doing just gradients through just one view. So by this, I mean that we want to estimate like similarity between this prediction network and representation of the second image, and we're doing it through cosine similarity. So and we do it like symmetric way.
This is the original Siamese network then, right?
Yes, it's original Siamese network. Yeah, we can say this way. So it's but like to make it work, there is like important step, and we will try to explain it in other slides. But right now the idea is like simple, that you have prediction network. So prediction network is basically you have to add to your encoder additional 3-layer fully connected network, and then you trying to maximize similarity between your so you want to maximize similarity between your prediction and representation of second view. But you can think of it like you want to take representation of first view and you want to project it to representation of second view. By this, you want to say that representation are the same. So like you basically want to find the object in the image. Like we want a cat, but like if you have a cat, then if you change color, it will be the same cat. But like it doesn't matter like what kind of distortion we have on the image. We have to just figure out what the object it is, and then you just combine this loss in symmetric way. So it just will be much more efficient in the sense that you're reusing your views and you have kind of 2 times more updates on your network.
So one more question before you go from this slide. Encoder blue. Excuse me.
You just said that after that, I would like to ask a question too.
Oh, okay. Yeah, sure. Just a quick one. Encoder produces some representation Z. Predictor
Yes.
produces what? Another representation of the same dimension. So you have to call it the same dimension, right? Why not just remove the predictor and have Siamese networks?
So the result is just like I will show it later in the slides, but it's basically they doing through evaluation. Like it's empirical like ablation study basically. But there are like some ideas that like I will show in later slides that we can interpret a SimSiam model as a expectation maximization algorithm. And they have some ideas why this prediction is important.
Yeah, Roger.
Yeah, so I'm trying to understand if there is something embedded in this type of diagram for SimSiam specifically. I'm wondering, can we do away with the right side, the encoder on the right side, and just draw an arrow from the output of the first encoder on the left and towards the similarity directly? Like, is it just the same network, the 2 encoders? Or is there something that is not obvious from the diagram that makes the 2 encoders different? I don't know.
The inputs are different, Roger.
The input is
Ah, okay.
So yes, so you
can
have
you clarify
image.
that? What's the difference?
Yeah. Okay, so you have image and you do 2 random dot documentation. So for example, I think it's like in first slide when I had a cat and I had like Photoshop, like some style, and yeah. So you have a cat, and second view will be photoshopped like cat. And through this schematic, you can see that you have representation of your X image in 2 ways. Like, and then you're using same encoder to get representation. You're basically treating as each image as a different image, and you're using same encoder because like you encode, like you're assuming like you have shared weights, and then you get a presentation for each image, and then you just want to understand kind of are they similar or not, like, and you want to like same like for same image, like you want to take two different views, and since they represent the same image but with different documentation, you want to attract them together. So this is the idea how you learn this representation.
Yeah, got it. Thank you.
Okay. Okay, so just like some results that this simple model like performs relatively well compared to previous state of the art. And you can see it requires even like smaller batch size than other like models as the BYOL, SwAV, and SimCLR, and achieves like comparable performance, and it doesn't need like any momentum encoder. So Mocha here is basically extension of SimCLR, which using momentum encoder, which is basically similar to BYOL in some sense. But the idea they're just like a bit different in the sense that in BYOL you don't need contrastive learning.
What is EP?
It's number of epoch. Like for example, for 100 epoch you can get this, and if you train it longer, you get high performance. Like you can train as much as you want. Like so, they usually like adapts to better. Like they usually kind of don't overfit, but they usually collapse. So collapsing, it means that like your optimization, like optimization task collapsed in the sense that it finds like a simple solution. So neural network figure out what is similar, what is not. So and a lot of this like problems will be considered like using negative pairs and momentum encoder. So all people trying to evaluate how not to collapse this Siamese network during optimization. Yes. Okay. And they're showing like better performance on transfer learning. So I would consider this method is kind of simple and gives you comparable performance with previous state of the art without using like complicated things. So this is what nice about this kind of work. Okay, next slide. Okay, so right now we will go through building blocks of this method, and we try to analyze what is important. So the most important step to avoid collapsing the solution, we need to use stop gradient, and we need to use stop gradient on a representation of second view, which we're trying to predict. So, and if you do that,
Explain what stop gradient is.
What is what?
What is stop gradient?
Okay, stop gradient means that you don't backpropagate through network. So if you have two views and one view passes through prediction network and you get this representation prediction, and second view gets this representation Z2. And so you backpropagating through prediction network only. You're not propagating for second view.
Interestingly, it used to be called freeze parameters, but okay.
No, you can't call it freeze because you're using same encoder every time. So you're just kind of answering representation, and so my idea is that like if you're not if you're doing backpropagation 2 times, network can kind of cheat in the sense that it can adapt weights simultaneously for your load, like for your similarity. So
Right.
You're
For
still updating
example,
the encoder. You're still updating the encoder.
yeah.
yes, but you have to anchor something, like anchor something. If you don't do it, you can like push your network to kind of collapse. Like in the sense,
network
it can.
It can get like 100% accuracy between similarities of representations if it just only predicts zeros for every image. And that's something that I can learn if for both views you get backpropagation. If you do backpropagation for both views, it could learn something like predicting 0, 0, 0, 0, 0 for the representation. And then the predictor network also predicts 0, 0, 0 always. And then you'll have perfect, your loss function will be 0, but the representations you're learning are not meaningful in any way. So that's one of the caveats of backpropagating 2 times through the same network.
So I guess another way you could put it is you're optimizing that similarity cost and backpropagation with backpropagation. And that means there are 2 branches through which the gradients propagate back. And one of them you just ignore. So you're not really quite optimizing the similarity. You have like incomplete gradients, and somehow, I don't know if there's theory behind it, but it improves the training performance.
So basically what I would say is, like Alex said before, if you have the 2 cat images, basically you're trying to predict like, okay, I see a cat image. What would the other view of the cat look like? That's what you're trying to predict from based on what you yourself will represent for another view of the cat. So for example, if you have 2 images for MNIST, for example, very simple, 2 6s, but one is slightly distorted and the other one is not, you still want them to have the same representation because they're both the number 6. So you're basically training yourself to predict the same representation with like a slight transformation. So the predictor network would be a small transformation between the 2 predictions because they're slightly different, but they shouldn't be too different. And basically you could say that the other view that you pass through this encoder that doesn't backpropagate, so it doesn't backpropagate through this encoder, you can see it as like a held out view that you can't train on. It's like training, you could create all of these augmentations beforehand and then selecting half of them and then having the rest as like a test set basically. So you don't backpropagate through those.
One issue with that explanation because the encoder is changing as you train, so you can't pre-compute.
But you could see it as like if you have a training set for each epoch, you can just generate like for 400 epochs, you can generate all different samples, right?
I think what I said still holds. I don't see the difference. I saw that the diagram means that the encoder is getting updated on both sides of the branch at the same time.
That's true.
But how? Like, there is there gradient flows only on the left, right?
Yeah, but yeah.
I understand that the networks share the same parameters, but from
let me just explain in the sense that we're dealing just like every time we're dealing just like with one sample. So our one sample doesn't have a relationship with any other data. When we do noise contrast estimation, we have one sample and we know like about all other samples. So the solution doesn't collapse in some sense because it kind of regularizes by other. So in the simple Siamese network, like you have just one sample at a time, and you want kind of maximize similarity. And neural networks say, oh, let's zero representation, make it 0, so we'll have high similarity. So and kind of in we'll see in future that like if you consider expectation maximization, like if you don't do the stop gradient, you probably collapse in even expectation maximization in some sense. So it's kind of so it's kind of you want like you have like gradients with respect different inputs, and like maybe you can find solution, like simple solution which collapses. Like maybe you don't need any information to make them similar, I guess. Like you
I
just
think,
have.
Rogers, what I think I mean is like, so what you do is you have like Alex said, you have one sample, you do an augmentation, and you don't train on the augmentation. So you don't back propagate for the weights of that augmentation. That's kind of what I meant as like a test set in a way.
Yeah, I
Parameters are
understand
shared.
that part. I understand, but the fact that you have to tell your automatic differentiation engine that it should not propagate the gradients through one of your branches, the one corresponding to your augmented input, means that you're not getting the full correct gradient for your cost function.
But
and I'm not saying it's wrong. I'm saying that it's just not exactly the same. You're optimizing something slightly different. You're taking just one view of your gradients, and it seems to be doing a good job. I was just wondering if there is theory to support that increase in performance.
I think the main idea here is that you're working through bottleneck. Like you have an image and you're like trying to compress it that much to the representation, and you just can like you don't have any control how you want to compress it. So I think if you you're giving like two different freedoms, you can compress and make them similar together in the same time, because prediction network has like this. So let's just move forward, and there's like building blocks on predictor and stuff. So okay. So what they noticed is like if you don't have this prediction network, even you use top gradient, it will collapse. Like this prediction network H kind of makes a difference in some sense. So if you have two encoders and even you do stop gradient, and you can calculate gradients, and you will see that gradients will be the same even without stop gradient. I'm
sorry.
Okay. So like this additional network, like H is important. And if it's fixed or it's like doesn't exist, like your gradients will be the same, even like you don't have stop gradient. So, and so there's like two tricks. You need this prediction network and you need stop gradient. Because otherwise your gradients will be the same, because it will be pure symmetric. So this H trying like give you some asymmetry in the sense. But maybe it will be clear from expectation maximization perspective. Okay, so they try different batch sizes. So you can see it doesn't require like super big batch size. It's more like regular supervised learning in the sense, but I think one note here is that batch size will also be influenced by optimization method you're trying to use. So I think they use just HDD, but you can use other high batch optimization methods. So one of them was in SimCLR. I don't remember the name, but you can try other optimization technique. But it's not most important thing, I would say, as a building block. And second, they also try to understand effect of batch normalization, because there was some like some research that people saying that BYOL doesn't work without batch augmentation, and they kind of trying to understand how much normalization influence architecture. And we can go next slide. And you can also try different similarity function, but it looks like similarity not the reason why solution can collapse. So here I would say that I think it's like the problem still is projection and how we do it. And if you give like freedom without stop gradient, and we have similar similar like projection, we probably will collapse. And so it's more like how you construct the problem. Okay, we can go next slide. So they also try to play with symmetry, but I would say symmetric case, like when you taking loss function for both views, it works better than if you just use one loss. We can go next slide. So they try to hypothesize why their method works. We can go next slide. So main idea is that we can do expectation maximization. Here in first line, you see expectation over L2 loss, which is will be equivalent to cosine similarity if you use L2 normalization and cosine similarity. And expectation maximization has two steps. So theta it will be parameters, and eta will be representation of an image X. So it's basically eta. But you can think of it, it's kind of average, like eta t of X, which is here, like in the end, it will be average representation of all images in your data set. Basically, you can see that if you do like if you're solving for theta, you have here eta t minus 1. So basically, stop gradient kind of creates your eta t minus 1. So that's why kind of stop gradient is important. Like if you just think through this one step update, you can see that like you do not propagate through this eta. It's fixed, and you update this eta just the next step, and your theta again fixed here. So it's like two-step optimization in some sense.
Could you clarify again what is theta and eta?
Okay, theta is the parameters of your model, and eta it's like you can think of a cluster or average representation of your image. Like we can go like classical way. Like you have two steps: you have cluster update and you have parameter update.
Okay, but you're talking about general expectation optimization. I thought you had mentioned that this is the same as or relates to somehow with Siamese, simple Siamese.
It's not related somehow. It's like I would say one-to-one, like in the sense that you have the loss here.
In that terminology, there's prediction and encoder. Which one is which?
So I would say this is a gradient descent, like the one you do when you have subgradient. So this you update the weights, and this will be representation.
So eta is what? The parameters of the predictor or prediction network?
This is yes. So encoder and prediction network, yes. It will be all together.
Wait, theta is the encoder, eta is the prediction network, or
yes.
what?
No. I mean, theta is parameters and eta is like, so it's like in classical machine learning, I would say it's like clusters. No, clusters is theta. Then, so eta should be so representation of the image. They called average representation of the image in this expectation in the end, and then if you want to make it Siamese, we can go next slide. Maybe it will be clear. So this eta will be basically second data augmentation. So here like might be some like confusions that the theta we can assume it's encoder parameters, but we also have prediction parameters. So I would say there's like you have to do like two-step optimization. Like in the sense, let's assume it's it just so let's assume there is no predictor yet, and just assumes that we have encoder and we have data augmentation. So data augmentation, it's this T.
So encoder is F, right? F sub theta is encoder.
Yes.
Okay, and T is your data augmentation.
Yeah. So you want to update. So I want to say that in latent like in latent space, your representation of two images is the same. And one should be fixed and one like should update. In kind of during iteration, like you kind of have a memory of previous step and you have future step which will update. And that if you have here like mean square error here, it's basically equal to cosine similarity, so there is no big difference because cosine similarity was normalized by L2 norm. And in next step, it will be, we can switch next slide. Okay, let's go on next slide. Okay, so here is predictor. So before Z, it's a Latin representation, and it was so representation is given by encoder F through of data augmentation of image X, and basically objective will be like this. So and then we get like optimal solution for this H prediction, like for H predictor. And you can see that like H kind of controls Latin representation of Z1. And that's why it kind of allows not to collapse, as I understand. But maybe it's better still to see like in gradients, but I don't think they write it down. Like they have just intuition why it doesn't work. But I think like if you go back on expectation maximization slide, you can see there is like two-step optimization, and this eta X it's represented by second view basically, and you have to put here probably H on top of this first element where you put X, and then you have like two different things. You have a prediction of average representation of other images in eta X, and then it shouldn't kind of collapse because you have to step and you have two different spaces.
Do you know if, I don't know, maybe in each batch, you have multiple augmentations of the same input image?
So if you have multiple documentation of each image, I think it's a multi-step alternation when you have like you can do for same image like different documentation. Then I think it won't change anything much. So
I'm thinking specifically of the update of data and then the update of data. Like if for the update on ADA, you have that expected value over T, which I think is the different augmentations.
I think
So to
that
me, it
augmentation doesn't. It shouldn't like influence you. Like that augmentation doesn't influence you. Like let's see this way. For example, we have encoder, we have that augmentation, and that augmentation like doesn't influence is that object or not. Maybe like if you think of latent space like manifold, for example, we have like some surface over cats, for example, and we have a cat, and if we have a cat and we can create encoder which kind of reduces this noise distortion. So all the cats with some distortion should like fall in the same point. And if you have this predictor network, you have a so it means that probably you have a representation of a cat a bit shifted by some like epsilon from the cat, and then this H kind of trying to get to the average of all this like cat representation in some sense. So, and
but in a batch, an average is just a simple average, right? And this is a simple average over multiple augmentations.
I don't understand completely what do you mean by average of the batch, because in batch you can have multiple different images, and like batch shouldn't influence your loss because you're working sample to sample. And second view will influence just as a symmetry. So
4 minutes. How many slides do we have? Just sorry for interruption.
Because I think I mean you will have average over batch gradients, like you have usually average. Yes, I agree with that. I just think that it doesn't influence optimization itself. Like your distance doesn't depend on any batch. It just it's like one-to-one. So I guess as an encoder neural network trying to take a sample and encode to some representation, and it might do like it's kind of network may be trying to understand the variation. So if it collapses, so it probably just the same. It can find solution like straight away, which like collapses all like two images to one point, and that's why it collapses. And this point also not constrained to any other like classes or other images. So it means like it can collapse everything to one point. So this way we don't learn like any information. We don't learn any like any factors of variation in the data. So this is my guess, that just because we're like not constrained and we need something like to constrain in the sense that there should be difference between sample in some sense. It's I think it's like more like it's not like in the sense that average of gradients. I just think it's like in the sense what exactly you do, like because noise contrast estimation usually doesn't collapse like this because you have like noise information which comes from other sample in the batch, and here you're like not restricted to do anything. Like you're not restricted to find like simple solution.
We continue discussion the next meeting when we'll talk about multiplicative interactions and where to find them. That's still on the list, right, Alex?
Yes, but I don't think it's related, but I can think.
Yeah, well, I thought that like that's what you kind of implied, that it kind of follows from. Well, anyways, it was a good overview and a good dive in as well, kind of simultaneously. So thank you both, Alex and Eloy, and we'll see everyone on at the next meeting with maybe not related, but the next topic. And I will ask everyone to contribute to the Google spreadsheet or Google Doc sort of again with sorting what we've planned, what comes next. But I'll bother you, everyone in the channel.